Hello, I am Paul Dean, a PhD student at Lancaster University, UK, and we're presenting our work into exploring the design space of emergent scheduling for distributed execution frameworks. Distributed execution frameworks like Apache Spark have become a popular solution for the execution of user-submitted jobs at a data center scale. As distributed execution frameworks provide an automated method to process terabytes of data across hundreds of nodes, autonomously deploying and executing long and short-term jobs, which when deployed create large simultaneous computations, for which these frameworks require data center compute resources to fulfill the scale of the submitted workloads. The scheduling of sporadic, large workloads, their individual jobs and subsequent tasks, creates a large overhead as each job and task requires a decision to be made. And then efficient scheduling is costly, applying a large overhead to submitted jobs in addition to the expected runtime of each process. These overheads result in additional power consumption across a set of nodes executing the given job. Previous approaches can be split into four categories. The first, general purpose approaches, use a single architecture or policy, providing a best fit for most workloads, and consider all available resources for each scheduling decision, providing high quality scheduling decisions that the entire cluster may be considered for the placement of jobs. However, this hinders the performance for latency-sensitive workloads, as there is a set of overheads applied to all workloads. The second, workload-specific approaches, are typically designed to schedule recent, diverging, and complex workloads for which a general-purpose approach is inefficient. This improves the end-to-end performance for a specific workload type, but limits the approach as there is a loss of performance for other workload types. Also, new frameworks may be required to regain lost general-purpose properties, for example, guaranteeing fairness. The next, hybrid approaches, offer the benefit of two specific scheduling approaches simultaneously, as a way to offer the capability of scheduling a wider workload set with a higher level of performance than general-purpose approaches. However, with hybrid approaches, available resources may be lost as they are split up to simultaneously manage two scheduling approaches. In addition, incorrectly selecting an approach adds additional overhead to scheduling decisions. Finally, learning approaches offer an efficient scheduling policy for workloads which have been presented during their training and are specifically tailored to these workload types. This offers a high level of performance. However, learning approaches are trained offline and require retraining when encountering new workloads, whereas adaptive approaches aim to provide one of a set of multiple scheduling policies or architectures at runtime, which may be switched out to better suit a given workload. However, adaptive approaches require user-provided parameters to inform scheduling decisions and adapt to unforeseen workloads. This highlights a key issue with both learning and adaptive approaches, where the handling of uncertainty is managed at the design phase of the framework. This can be seen with the need for offline training and learning approaches, and the need for domain-specific knowledge in adaptive approaches. Therefore, we aim to manage uncertainty at runtime and learn which scheduling approach best fits each workload as they are encountered in deployment. We use an emergent systems approach, assembling a system from a set of fine-grained building blocks, where some blocks have variation in their behavior, such as different scheduling policies. This provides a set of alternate compositions that we can adapt between at runtime, while learning online which composition best matches each set of deployment conditions encountered. So we could form composition A initially, and switch to composition B should deployment conditions change and composition A be a poor choice. This raises the following research questions. What are the dimensions of compositional adaptation in self-adaptive distributed execution framework schedulers? Do different distributed execution framework workloads correlate with different ideal policy compositions? And if so, how? And if yes to the previous research question, can we identify points in a workload at which it is rational to adapt between different scheduler compositions? In answering these questions, we are met with uncertainty dimensions as we encounter potentially unknown workload completion times, varying even from jobs of the same time. The sporadic arrival of workloads and independent job submissions create different sets of workloads to handle. And the initially unknown data exchange costs of running jobs, which would add overhead to both nodes and their interconnections. All of these dimensions provide challenges in understanding when adaptation should take place. The architecture or approach is centralized and similar to previous distributed execution framework architectures. Workloads submitted to the resource manager consist of a set of jobs, each requiring their own data source and task definitions, which form the executable process for each job. The resource manager controls the allocation of resource containers for the cluster, deciding what resources each job is provided for its execution lifetime. The node manager controls the setup of application masters, which schedule individual tasks of a given job, and requests executors from the resource manager, which complete the execution of tasks within their allocated resources. The resource manager and node manager are emergent systems constructed at runtime. This begins with the passing of the app interface to the framework and discovering all variations. In this example, we see the components available to build a valid resource manager. Once we know which components are available, individual compositions may be made with differing behavior. In this example, each of the scheduling policy behaviors have formed their own unique composition, which may be adapted at runtime. To answer our research questions, we performed a set of experiments using 15 synthetic workloads. This consisted of 5 coarse, fine, and mixed workload types. Each workload contained 20 individual jobs, and each job had 40 tasks. 4 different scheduling policies were selected. The first is FIFO, a simpler and commonly used scheduling policy, offering little overhead at the cost of more informed placement decision, and is used in existing frameworks such as Apache Spark and Sparrow. Naive fair thread and naive fair memory offer the guarantee of fairness for a specific resource type, and are used in popular frameworks, for example Yarn. Finally, dominant resource fairness was selected, as the policy takes a more detailed look at resource usage for a tighter control of fairness and reduces issues of oversaturating resources due to previously scheduled jobs. In the experiments, the scheduling policies were subjected to each workload recording the total runtime. The experiments were performed within a real data center environment across a 5-node cluster. The graph displays results for all workloads for all schedulers, with the recorded average runtime results for each workload presented for each of the 4 scheduling policies. We can see that FIFO is able to complete the coarse and fine-grained workloads more efficiently, with FIFO completing fine-grained workloads 20% faster than naive fair thread, a significant reduction in the resources required and overall power consumption. However, mixed-grained workloads are completed more efficiently by naive fair memory, demonstrating that there is not a single scheduler which may be used across all workload patterns presented, and a need for adapting to different workloads encountered. The next graph presents the results for each scheduler subjected to CGW3 workload, showing the individual job runtime for the workload, with the x-axis also showing the ordering of the workload's duration over time from the initially given job CG21 to the final job CG40. Overall, FIFO is the best choice of the 20 jobs. In the workload, FIFO completes 7 the fastest and is almost the fastest for the furthest 6. However, this means there are 7 jobs within the workload which FIFO perform poorly, and that periods exist during the workload where other scheduling approaches prove to be a better choice. This is most notable for apps CG26 to 28, where naive fair thread proves to be a better choice, and apps CG34 to 36, where the NFT scheduler again provides a notable performance improvement. This shows points within the workload for adaptation to be performed for an increase in efficiency. The next graph displays the results for the workload MGW3, again displaying the individual job runtimes for the workload. Overall, naive fair thread proves to be the better choice for the workload, completing 6 of the 20 workloads more efficiently. However, there is again a period within the workload where another scheduler will provide improved performance. This is between app FG184 and 109, where after a set of coarse-grained jobs, we find that naive fair memory would prove to be a better scheduler for this block of fine-grained jobs, offering improved efficiency. Although this raises an underlying uncertainty of the long and short-term effects of scheduling decisions, and that the improved performance seen is the effect of an earlier scheduling decision, and is an effect that would need to be considered in deciding when to perform adaptation. As our results showed in answering our research questions, as we were able to see the divergent points between schedulers and different workload types, we see potential performance gains from adaptation and see while there are difficulties within scheduling for one workload, there is the potential for improved performance too. The exploration of these results provided insight for adaptation, presenting two key points where adaptation may be performed. The first is the resource manager, which provides identifier job properties for profiling workloads, and the second is a feedback point from the execution performance of jobs, which may inform mid-workload adaptations. Finally, future work looks to explore self-adaptive control strategies, applying learning agents to the Emergent scheduler, employing multi-tier scheduling, where adaptation may be performed at a resource manager and application master level simultaneously. And finally, adaptation of schedulers at runtime, adaptation of the scheduler's architecture at runtime. For example, adapting to a decentralized architecture for lower latency in scheduling decisions. This is different from the presented work, which is solely focused on adapting scheduling policies within a centralized architecture. This concludes the presentation. Thank you for listening.